This video will go through key examples in Packet 2.6. The first example we're going to take a look at is number 15. Write the equation for the line tangent to f of x at x equals 16 using problem 12 above. So using problem 12, we know that f of x is equal to the square root of x. We also found f prime of x, the derivative, when we did that problem, and it was 1 over 2 square root of x. So we have that information coming into 15. If you weren't given f prime of x, you would need to find it for this problem. Anytime you are trying to find the equation of a tangent line, you need a point on the graph on f of x, and you need the slope of the tangent line at that point, at whatever your x value is. So we already have f prime of x. The way we find the slope of the tangent line at x equals 16 is we substitute it in. So here I'm going to substitute in 16. So we get 1 over 2 root 16, which is 2 times 4 in the denominator there, so it's 1 over 8. That is our slope for the tangent line. Then we need to find the point on f of x where x is 16. For that, you're going to use f of x, and you plug 16 in. So f of 16 is the square root of 16, which is 4. That gives you a point at 16, comma 4. That's our x value and our y value. Okay, now we're ready to write the equation of the tangent line. We can just write it in point-slope form. This is the generic form. It could always be rearranged into slope-intercept form later if the problem asks you to do that. So I have y minus y1, so I'm plugging in the y value from my point, that's 4, equals the slope we got from the derivative, it was 1 over 8, and then x minus our x value, or x1 value, which was 16. And that is the equation of the tangent line. You could do that process with any of the problems above. And there are plenty of practice problems on this in this packet. Next, we're going to look at a related but slightly different type of problem. It says, let f of x equal x to the fourth and g of x equals x to the third. At what value of x do the graphs of f and g have parallel tangent lines? Well, to have parallel tangent lines, the tangent lines must have the same slope. So that means we're looking for the same derivative, at least at one point. Let me rewrite this. The same derivative at a given x value, and we'll just call it x equals a. So that means we want f prime of x to equal g prime of x. We're going to solve for the x value where that statement is true. In order to do that, we have to find the derivative of these problems. So for f, we've got x to the fourth. When I take the derivative, I get 4x to the third. When I take the derivative of g, which is x cubed, the derivative is 3x squared. And now we need to solve for x. And now this becomes an algebra or pre-calc problem. What we do, we don't divide by x here, or x squared, because you would get rid of a possible solution. What we need to do is get the terms on one side, factor, and solve. So I'm going to subtract 3x squared from both sides. You get 4x cubed minus 3x squared equals 0. Factor out the common multiple with the common factor here, the GCF, that's an x squared, and you're left with 4x minus 3. Now, we solved a lot of problems like this in previous math classes. You take each factor and set it equal to 0. So you've got x squared equals 0, and you've got 4x minus 3 equals 0. And then solve. So for x squared equals 0, I'm going to solve by taking the square root of both sides. That gets x alone. It's x equals 0. For 4x minus 3 equals 0, I'm going to add 3 to both sides. Whoop. And I get 4x equals 3. Divide both sides by 4. You get x equals 3 over 4. So both of these are solutions to the problem. It says at what value of x do the graphs of f and g have parallel tangent lines? That means there are two places where the tangent lines are parallel, at x equals 0 and at x equals 3 over 4, because the derivatives are the same at those points for both f and g. So the slope of the tangents is the same, making the tangents parallel. All right. There are practice problems in the packet now. And then our next type of problem is here on page 4. This is really a similar idea to the problem we just did with parallel tangent lines. This one, though, is about horizontal tangent lines. So the question here is, when does a function have a horizontal tangent line? Horizontal means it's flat, moving left to right like this. To have a horizontal tangent line, the slope would need to be 0. So to figure out where a function has a horizontal tangent line, we have to set the derivative equal to 0. So in this problem in 3, this example, I'm going to find the derivative first. So f prime of x, make sure you label that. 4x squared, I'm going to bring down the 2. So we've got 4 times 2x to the 2 minus 1 plus 7x to the 1 minus 1. That's going to give you x to the 0, which is the same as 1. So this just ends up being a 7. And then minus 13, the derivative of any constant is just 0. So the only part here was this multiplication. Didn't really look like multiplication there. This is 8x plus 7 for the derivative. So now we set the derivative equal to 0. So this is when the derivative is 0 is when you have a horizontal tangent line. Subtract 7 from both sides. I get negative 7 equals 8x. Divide both sides by 8. You get negative 7 over 8 equals x. So looking at this graph, we can see this actually is not an accurate graph for f of x. If we were to graph f of x, it would be a quadratic. So it would look something like this. And right here at negative 7/8 is where the tangent would be horizontal. This other graph that I have up here is meant to help us see on graphs where you're going to have a horizontal tangent line. Horizontal tangent lines occur when you go from increasing to decreasing. So at that relative max, you end up with a horizontal tangent line, essentially a slope of 0 at a relative max. Same thing at a relative min. You're going to have a tangent line with a slope of 0 here. Okay, our next example is on normal lines. Normal is the equivalent of perpendicular. So if it asks you about a normal line, it really means a perpendicular line. So this is like a tangent, but instead of brushing the graph and showing the slope at that given point, the normal line goes through the point that would be the point of tangency, but it gives you the perpendicular slope or the opposite reciprocal slope. So in order to figure out a normal line for f of x here, this is the correct graph of f of x, at x equals 3, so right here, if we were to graph the tangent line, it would look something like this. We're going to be looking for the line that's perpendicular to that tangent, to that slope there. So we're looking for an equation for this line that goes through that same point but is perpendicular. So once again, we have to start by finding the derivative, f prime of x. Bring down the 3, you get 3x squared minus 8x plus 1. So remember, for the part that's just linear, it's the slope that is the derivative. For plus 3, the derivative of a constant is 0, so that disappears. So this is our derivative. Then we want to find the derivative specifically at x equals 3. So we're going to plug in 3 times 3 plus 1. So we get 27 minus 24 plus 1. That gives us 4. So f prime of 3 equals 4. This is the slope of the tangent line. So I'm going to call this M tangent. If we want the normal or perpendicular slope, you take the opposite reciprocal of that. So instead of 4 over 1, we get negative 1 over 4. So that's the slope of our normal line. But just like for a tangent line, for a normal or perpendicular line, you need a point in addition to the slope. So luckily we have a graph here, and we can see where that point is. It's at 3, negative 3. So I'm going to write 3, negative 3. If you didn't have a graph, you could plug in x equals 3. So you'd do f of 3 and go back to this original equation. So you'd have 3 cubed minus 4 times 3 squared plus 3 plus 3, and you would get negative 3. Okay, so that gives us a point at 3 comma negative 3. We are now ready to write the equation of the line. So as always, it's y minus y1 equals m, and I'm going to write for perpendicular times x minus x1. So substituting in what we found, your y1 is a negative 3, our slope was negative 1/4, our x value is 3. So simplifying, we get y plus 3 equals negative 1/4 times x minus 3. And that is the equation for our normal line, or for the line that is perpendicular to the tangent. The final piece of information for this video, moving to the second to last page, this page 6, we can find tangent lines and normal lines for trig functions and for exponential functions, just like we did for the functions we've been looking at in the rest of this video. We just have to use derivative rules that do not include the power rule. So we've already learned these, but this is a quick reminder. The derivative of cosine is negative sine of x. The derivative of sine is cosine of x. The derivative of e to the x is e to the x. The derivative of the natural log of x is 1 over x. This is another way to write it to show that it's a logarithm with base e, but the derivative is the same. It's 1 over x. So you can do the same types of problems where you're looking for derivatives, where you're solving for a derivative at a specific point, or where you're doing tangent or normal lines like we did in previous examples and problems. And that's it for this video.